I need to know what to do.
The first problem I'm going to look at is I want to try to find all of the zeros of this polynomial function. And this is going to be a fifth degree polynomial function. 2x to the fifth plus 1x to the fourth plus 9x squared minus 32x plus 20. So we're going to try to find all the zeros of this fifth degree polynomial. Now, I have a question. If we were back in beginning algebra, elementary algebra, ladies and gentlemen, do you think we could factor this polynomial? Do we have anything in our arsenal in elementary algebra to factor that polynomial? What do you think?
No.
Nothing. There would be nothing that an elementary algebraic student could do to factor that polynomial, ladies and gentlemen. But we're not only going to show you how to find all the zeros of this fifth degree polynomial, we're going to show you how to factor this thing completely down into the product of nothing but linear factors. And so we've come a long way since our days in elementary algebra. Okay. All right. So here we go. First of all, I am going to compose a list of potential rational zeros. By using the rational zero theorem, ladies and gentlemen. The rational zero theorem. Now, what does this word potential mean here? Potential.
It's not confirmed, but it's a possibility.
Yeah, it's a possibility. So the list that I'm about to compose here of these rational zeros, it's a list of potential rational zeros, meaning, ladies and gentlemen, meaning that all the rational zeros I list here are not necessarily going to be rational zeros of this function. The rational zero theorem guarantees that if this polynomial function has a rational zero, it may not, but if it does, it must come from the list that I'm about to build here. Okay, that's what that rational zero theorem is saying. So first of all, to build this list, we form our P list, ladies and gentlemen. Our P list constitutes factors of our constant term. So what are factors of positive 120, of positive 20, excuse me, positive 1 and positive 20, or we could have negative 1 multiplied by negative 20. We could have a positive 2 multiplied by a positive 10, or we could have a negative 2 multiplied by a negative 10. 3 don't go into 20 evenly, 4 does. We could have a positive 4 times a positive 5, or we could have a negative 4 multiplied by a negative 5. So this P list constitutes all the factors of the constant term of our fifth degree polynomial, all the factors of positive 20. Now we're going to form a Q list. And this Q list represents all factors of the leading coefficient, positive 2. So the only factors of positive 2 would be 1 and positive 2, or negative 1 and negative 2. Now we're going to form what's called our P over Q list. Our P over Q list is formed by taking each value in the P list and dividing it by each value in the Q list. So positive or negative 1 divided by a positive negative 1 is going to give us what? What's a positive
1.
negative 1 divided by positive negative 1?
1.
It's going to be positive or negative 1. Do you agree? Isn't that true? Because ladies and gentlemen, we could have a positive 1 divided by positive 1. That's 1. We could have a negative 1 divided by positive 1. That's negative 1. We could have a positive 1 divided by negative 1. That's negative 1. Or we could have a negative 1 divided by negative 1. Do you agree? Which is what? Positive 1. Everybody see what's going on here? So when you have a positive or negative 1 divided by a positive or negative 1, it's either going to be a positive or a negative 1. Isn't that true? Got to be a positive or negative 1. All right. So positive negative 1 divided by positive negative 1 is positive negative 1. Positive negative 1 divided by positive negative 2 would give us positive negative 1/2. Positive negative 2 divided by positive negative 1 is positive negative 2. Positive negative 2 divided by positive negative 2. What's positive negative 2 divided by positive negative 2?
Positive negative 1.
negative 1.
Positive negative 1, which we already accounted for, so you don't have to list it again. And then you got positive negative 4 divided by positive negative 1, or positive negative 4 divided by positive negative 2. But what's positive negative 4 divided by positive negative 2?
Positive negative 2.
We've already accounted for positive negative 2, so they don't have to list that again. Move onward. Positive negative 5 divided by positive negative 1. Positive negative 5 divided by positive negative 2 is positive negative 5/2. Positive negative 10 divided by positive negative 1 is positive negative 10. Or positive negative 10 divided by positive negative 2, but positive negative 10 over positive negative 2 reduces down to positive negative 5. We've already accounted for that. Positive negative 20 divided by positive negative 1 is positive negative 20. Positive negative 20 divided by positive negative 2 is positive negative 10. We've already accounted for that. All right. Ladies and gentlemen, the rational zero theorem, what does it say? It says if, that's a big if f of x, our fifth degree polynomial function, has a rational zero. If it does, it may not, but if it does, if it has a rational zero, then it must come from what list? What list does it have to come from?
P over Q.
The P over Q list. That's what the rational theorem is saying. The rational theorem is not saying that all of these are rational zeros of f of x. In fact, they could not be all rational zeros of f of x, because how many do we have here? 2, 4, 6, 8, 10, 12, 14, 16 of them. Ladies and gentlemen, there was a theorem, the fundamental theorem of algebra guarantees that this is only going to have 5 zeros. It's only a fifth degree polynomial. So it cannot have all these as rational zeros. The rational zero theorem doesn't say that. It says that if f of x, this fifth degree polynomial, has a rational zero, it must come from this list. So I have a question for you. Could 6 be a rational zero for this polynomial function? Could 6 be a rational zero?
No.
It cannot be, because 6 is not my P over Q list. You see that? 6 cannot be a rational zero of this thing, because it's not in his list. Could 3 be a rational zero of this polynomial? 3?
No.
No, 3 is not in this list. It's not a rational zero. Okay. All right. Now, so how are we going to find these rational zeros of this fifth degree polynomial? All we know is we have a list of potential rational zeros. Well, here's where a little bit of trial and error comes in, ladies and gentlemen. What we need to do is we need to judiciously choose values from this list and see if they are zeros to this polynomial function. Now, instead of plugging in the values for x and then, going through and seeing if we get 0, the easier way to determine if any of these rational numbers are zeros is to use synthetic division. It's so much quicker, and use the rational and use the remainder theorem that we seen 2 days ago. So we need to, choose one of these and then synthetically divide it into the coefficients of this polynomial, and hoping that we do get a 0 remainder, because if we get a 0 remainder, we will have found a 0. Okay. Now, which ones do you start with? Well, here's a rule of thumb. Over the years, I've discovered, ladies and gentlemen, that you always want to try the simple ones first. Always try positive and negative 1 first. Usually one of them works. One of them is a 0. I'm not saying always, but usually it seems like the simple ones, provide at least one of your zeros. So don't try the fractions until you try like the easy ones, like positive or negative 1, positive, negative 2. Okay, reserve the fractions for last. All right. All right, so I'm going to choose positive 1 here, ladies and gentlemen, and I'm going to see if it's a 0 of my polynomial function. Well, first of all, I'm gonna purposely choose -1, okay? So here's what I'm gonna do. I'm gonna see if -1 is a zero of this 5th degree polynomial function. So I'm gonna synthetically divide -1 into the coefficients of this polynomial. That's to say the coefficients are 2, 1, 9, -32, and 20. If I was missing a, wait a minute. In fact, I am missing a, what degree term am I missing in here?
Third degree.
I'm missing a 3rd degree term in between my what? 4th degree term and 2nd degree term. Because of that, ladies and gentlemen, we must insert what's called a placeholder. So we will insert the coefficient of 0 to be the placeholder of the 3rd degree term's coefficient. All right, so our coefficients are going to be 2, 1, 0, 9, -32, and 20. Let's put those into our synthetic division bar here. 2, 1, 0, 9, -32, 20. And now we're going to find out if -1 is a 0 for this polynomial function. Bring down to 2, we multiply, bring the number up and add. Multiply, bring the number up and add. What's -1 times 2? That's -2, bring the number up and add, and you get -1. -1 times -1 is +1. 0 plus 1 is 1. -1 times 1 is -1, bring the number up, add. 9 plus -1 is 8. Multiply, -1 times 8 is -8, bring the number up, now add. These add to -40. Multiply, -1 times -40 is 40. Add. Ladies and gentlemen, do I get a 0 remainder?
Nope.
Notice my remainder is not 0. Because my remainder is not 0, ladies and gentlemen, -1 is not a 0 of my polynomial function f of x. It's not a 0 because we did not get a 0 remainder. What other one do you think I should try? -1 doesn't work. It's not a 0. What other one do you think would be the wise one to try, ladies and gentlemen? Pick a nice one, easy one. I tried
2.
-1. -1 don't work. Hey, how about just try +1? -1 is not a 0, but how about +1? Let's try +1. Let's see if it's a 0 to this 5th degree polynomial function. Hence, I'm going to try to divide +1 into the coefficients. Does anybody have the coefficients written down so I don't have to flip my paper over?
Yeah, so it was 2, 1, 0, 9, -32, and 20.
And 20. Thank you. All right, here we go. We're gonna divide synthetically 1 into our coefficients of our polynomial, and we'll see if we get a 0 remainder. If we do, 1's a 0. If we don't get a 0 remainder, 1's not a 0. 1 times 2 is 2. Bring the number up and add. 1 plus 2 is 3. 1 times 3 is 3. Bring the number up and add. You always add, and you get 3. 1 times 3 is 3. Bring the number up and add. 9 plus 3, 12. 1 times 12 is 12. Bring the number up and add. You get -20. 1 times -20 is -20. Bring the number up and add. And bingo, we get a 0 remainder. And ladies and gentlemen, because we get a 0 remainder, we would conclude that what? 1 is a what?
0.
1 is a 0 of our polynomial function. We found a 0. 1's one of them. Once you crack the ice with one of them, usually the other ones they come easier. Okay. Now, notice I leave behind this quotient polynomial here, right on after performing synthetic division. To find other zeros of this polynomial function, you can use what's called repeated synthetic division. For instance, I could pick up where I left off here, and I could choose some other number from my P over Q list and see if it, gives me a 0 remainder. Does anybody remember one of our theorems that says that these zeros may not be unique, meaning that they could be what, repeated? Do you remember one of those?
Yes.
So you know what, ladies and gentlemen, 1 conceivably could be a 0, not 1 time, but 2 times. In other words, 1 could be a 0 of maybe multiplicity of 2. So feel free to try 1 again. All right, bring down the 2. 1 times 2 is 2. Bring the number up and add, and we get 5. 1 times 5 is 5. Bring the number up and add, and we get 8. 1 times 8 is 8. Bring the number up and add. 12 plus 8 is 20. And 1 times 20 is 20. And we add, and bingo again, les amis, we get a 0 remainder. And since our remainder is 0 again, we would conclude then what? That 1 is a 0 again. 1 happens to be what's called a repeated 0 of this 5th degree polynomial function. 1's a 0 again. Now, so we found 1 to be a 0 again, correct?
Yes.
Let's see. All right. So we got our polynomial down to a 3rd degree polynomial here because we did 2 divisions. We divided x minus 1 into our 5th degree polynomial, and we got our quotient. We then divided x minus 1 in again and got a smaller quotient. This is down to a 3rd degree polynomial by the time we're down here. We started with a 5th degree. Its degree was knocked down by 1 to a 4th degree, knocked down by 1 by another division down to a 3rd degree. We got it down to a 3rd degree polynomial. But, les amis, I don't know if a 3rd degree polynomial can be solved from this point onwards. Maybe it can be. Maybe we do not have to use, synthetic division again to find another 0. In other words, we might be able to stop here and then recover our remaining quotient, which is to say our remaining quotient would be 2x cubed plus 5x squared plus 8x plus 20. And if I set this polynomial equal to 0, I would have to find 3 more zeros from it. Do you agree? See, we already found 2 zeros. 1's a repeated 0. 1 occurs with multiplicity of 2. So we found 2 zeros. We have to find 3 more. Remember, there's got to be 5 zeros to this 5th degree polynomial. But I have a question for you. Can I factor this left side? Can we solve this 3rd degree polynomial equation by factoring the left side? And if so, what factoring method do we employ here, les amis, from basic algebra?
Grouping.
The grouping method. It's a 4-termer. So let's try grouping. So I'm going to throw parentheses around the first and last 2 terms. Notice there's no sign adjustment necessary for the last term because we have a positive sign in front of our 3rd term here. Okay. Now, what can I factor out of my first 2 terms here?
2x or x squared, sorry.
Just x squared. And what do we leave behind when we factor x squared out?
Plus 5.
2x plus 5 plus, and then what can I factor out of the last terms?
4.
4. Hoping to leave behind the 2x plus 5, do we? Kind of looks like it. Looks like grouping is going to work. Now we can factor out the 2x plus 5 since it's a common binomial factor of both terms, times what would I leave behind?
2x plus 4 or x squared plus 4.
X squared plus what, 4? All right, everybody see that there? All right, ladies and gentlemen, look at, we completely factored the left side of this 3rd degree equation. So now we can set these factors equal to 0 and then solve for x. We can recover our 3 remaining zeros for this 5th degree polynomial. Solving this equation for x, we minus 5 from both sides and then divide both sides by 2. So another 0 is going to be what? Negative 5 halves is a 0. Hey, by the way, does negative 5 halves come from our P over Q list? Is it in there?
Yes.
The rational 0 theorem, it better be. And it is. Look at that. Negative 5 halves is a rational 0. And it's in our list. The rational 0 theorem guarantees that it has to be in that list. Okay. All right. So now to find the other 2 zeros, we set this other factor, x squared plus 4 equal to 0. And now we got to solve this equation. Well, this is a quadratic equation, and there's many ways to solve quadratic equations. Probably the quickest, easiest way to do this one is to use the square root method. So we isolate the squared term on the left by subtracting 4 from both sides. And now we take the square root of both sides of our equation. And ladies and gentlemen, we get our other two zeros, which says our other two zeros, x must be positive or negative what?
2.
2 what? These are not real.
2i.
Yeah, 2i, right? These are imaginary roots now, or imaginary zeros. 2i. And you got your other two zeros. So 2i is a 0 and negative 2i is a 0. What theorem, ladies and gentlemen? You remember a theorem that guarantees that if you get an imaginary or complex 0, they must always come in conjugate what?
Pairs.
Conjugate pairs. Do you agree? Remember that theorem? That's why if 2i is a 0, it's a guarantee and an automatic to say that negative 2i is a 0 and vice versa. How many zeros did I find here?
4.
1, 2, 3, 4, 5. 5 zeros. 5 zeros for what degree polynomial? For a 5th degree polynomial. And the fundamental theorem of algebra guarantees that you're going to get 5 zeros to a 5th degree polynomial. The theorem does not say they're all going to be real. Some could be imaginary or complex, but you got to get 5 zeros. Or, ladies and gentlemen, that theorem is guaranteeing that the sum of the multiplicities of all these zeros must be equal to what? 5. So we would say that 1 is a 0 of multiplicity of 2. Everybody see the notation? 1 is a 0 with multiplicity of 2. In other words, it's a repeated 0 and it repeats 2 times. Negative 5 halves is a 0, and positive and negative 2i are zeros. And there you go. There's your list of zeros for this polynomial function. Okay? 5 zeros. Where the sum of the multiplicities add up to 5. 2, this has a multiplicity of 1. These zeros have a multiplicity each of 1. So 2, 3, 4, 5. The sum of the multiplicities must be equal to 5, and that's the case. Everybody see that there? All right. Not only have we uncovered all the zeros of this 5th degree polynomial function by the factor theorem there and by the linear factorization theorem, it must be true then that our 5th degree polynomial f of x would have to factor into x minus 1 times x minus 1. Do you agree? Didn't the factor theorem say 2 days ago that if 1 is a 0, then x minus 1 has to be a factor? Wasn't that true? So if 1 is a 0 occurring twice, then x minus 1 and x minus 1 have to be factors of our polynomial. Negative 5 halves is a 0, so x minus a negative 5 halves would have to be a what? Factor. And if 2i is a 0, x minus 2i must be a factor. And if negative 2i is a 0, x minus a negative 2i must be a linear factor. We have completely factored that 5th degree polynomial down into its product of linear factors. So it would be x minus 1 quantity squared times x plus 5 halves times x minus 2i times x plus 2i. And there you go, ladies and gentlemen. Not only did I promise you we're going to find all 5 zeros, which we have, but I also guaranteed or promised you I was going to be able to factor this polynomial down into nothing but linear factors, and we have done that. If you were to take the time and multiply all this back out and gather together all your like terms, you would get back your 5th degree polynomial function. Okay? That makes sense what we just did with that problem? So to recap, we wanted to find all the zeros of this 5th degree polynomial. To do that, we used the rational zero theorem in putting together our P list, Q list, and our P over Q list. The P over Q list being the list of potential rational zeros. We then chose values out of this list and synthetically divided them into the coefficients of our 5th degree polynomial to see which ones were zeros. And of course, the ones that are zeros are the ones that are going to give you a remainder of 0. Okay. And we discovered that 1 did give us a remainder of 0, not once, but what? Twice. So 1 is a 0 with multiplicity of 2, or occurs 2 times. We then picked up where we left off, and after two divisions, we then were able to solve this third degree polynomial equation using basic algebra methods, factoring methods, and we recovered all the other remaining zeros there. And we are done with this problem. Okay, any questions, ladies and gentlemen? Welcome to section 3.4. Okay. All right. Maybe we could try another one, huh? All right, I'm going to go down to the problems here. Let's see here. All right, problem number 18. I want to look at that one there. For number 18, it says find all the zeros of this fourth degree polynomial function. Number 18. This is number 18 in your textbook on page 341. Number 18 on page 341. Try another one. So our polynomial function is d of x, which is a fourth degree polynomial function, 3x to the fourth, minus 2x cubed, minus 21x cubed, minus 21x squared, rather, minus 4x plus 12. How many zeros am I going to have to this fourth degree polynomial function when I get done?
4.
We're going to have 4 of them, correct? There better be 4. We could have some repeated zeros, and we may not all, they may not all be real zeros. Some could be imaginary, some could be complex, but there better be 4 of them total. The multiplicities of all the zeros better sum up to 4, according to the fundamental theorem. All right, ladies and gentlemen, now to find these zeros here, we could maybe again use the rational zero theorem to help us get started. The rational zero theorem says that, or guarantees that, if this thing has a rational zero, it must be of the form of P over Q, where P constitutes all the factors of the constant term. So what are factors of 12? Plus or minus 1 times plus or minus 12, plus or minus 2 times plus or minus 6, plus or minus 3 times plus or minus 4. Those are all the factors of positive 12. What are all the factors of the leading coefficient? That'll be my Q list. What's all the factors of 3? Positive negative 1 times positive negative 3. Now we can form our P over Q list, which gives us the list of potential rational zeros of this polynomial function. So we could have positive or negative 1 divided by positive negative 1, which is positive negative 1. Positive negative 2 divided by positive negative 1, which is positive negative 2. In fact, all of these divided by positive negative 1 is just going to duplicate the P list. But we could have some fractions. Positive negative 1 divided by positive negative 3 is positive negative 1/3. Positive negative 2 divided by positive negative 3, positive negative 2/3. Positive negative 3 divided by positive negative 3 is positive negative 1. We've already accounted for those. Positive negative 4 divided by positive negative 3. Positive negative 6 divided by positive negative 3 reduces down to positive negative 2. We've already accounted for those. Positive negative 12 divided by positive negative 3, positive negative 4. We've already accounted for those. All right. So the rational zero theorem guarantees that if this polynomial function has any rational zeros, they must come from this list. Which one do you want to try first, ladies and gentlemen? Which one do you want to try first here?
1.
All right, let's try positive 1. Try the easy ones first. I mean, you could try the fractions, but, always try the easy ones first. Sometimes these fractional ones are zeros, don't get me wrong, but it's sure nice to try the easy ones first. All right, notice I put the coefficients of my polynomial in my synthetic division bar. I'm not missing any powers of x, so we do not need any placeholders in here. And here we go.
Should it be -4?
Probably. Yep, -4. All right, I better check things over one last time before we dive in. All right, here we go. 1 times 3 is what? 3. -2 plus 3 is 1. 1 times 1 is 1. Add these together, you get negative 20. 1 times negative 20 is negative 20. Add these together, we get negative 24. 1 times negative 24 is negative 24. Add these together, you get negative 12. Ladies and gentlemen, unfortunately, we did not get what? A zero remainder, correct? So the remainder is not equal to 0. So therefore, 1 is not a 0 of this 4th degree polynomial function. Any other choices? 1 don't work.
Negative 1.
Try negative 1. Negative 1 is easy to work with. So you may need some scrap paper later on as you go through a little bit of trial and error here, or an eraser, however you want to treat this. Negative 1 times 3 is negative 3. Add these together, you get negative 5. Negative 1 times negative 5 is 5. Add these together, you get negative 16. Negative 1 times negative 16 is 16. Add these together, you get 12. Negative 1 times 12 is negative 12. And yes, we do have a 0, ladies and gentlemen. We got a 0 remainder. Notice our remainder equals 0. So therefore, negative 1 is a 0. So we found a 0. We cracked the ice. Negative 1's a 0. Now, we started with the 4th degree polynomial, and by dividing out x minus a negative 1, which is meaning we really divided out the binomial factor of x plus 1, we got our quotient polynomial down from a 4th degree down to a what? 3rd degree. So this would be 3x cubed minus 5x squared minus 16x plus 12. Do you think grouping would work here, ladies and gentlemen? Look at, all you got to do is look at this. What could you factor out of the first 2 terms here? Nothing. What can you factor out of the last 2 terms? Well, 4. 4, do you agree? But I don't think grouping would work here if we try to use grouping to factor this. Do you agree? If you try to use grouping on this, I don't think it's going to work. So you can use repeated synthetic division if you want. What do you want to try next? We can divide into what remains. You can keep going. It's called repeated synthetic division. You want to choose another number out of here, or you want to try negative 1 again, or try another number, or what?
3.
Try 3. 3 times 3 is 9. Add these numbers together, you get 4. 3 times 4 is 12. Negative 16 plus 12 is 4. 3 times 4. Wait, this would be negative 4. Yeah, negative 16 plus 12 is negative 4. 3 times negative 4 is negative 12. And you're right, we do get a 0 remainder. And so, as it turns out, 3 is a 0. 3 works. So we found 2 of our 4 zeros. Now there's going to be 2 more, but look at, by now we got this down to a what degree polynomial? We've done 2 divisions on a 4th degree polynomial. We've divided out 2 linear factors, ladies and gentlemen. So we got this down from a 4th degree down to a what?
2nd degree.
It's down to a 2nd degree polynomial. So what remains here is 3x squared plus 4x minus 4. And you agree that we could probably find the other 2 remaining zeros by setting this equal to 0 and just solving this quadratic equation? You could use repeated synthetic division if you want. You can try synthetic division again, try to hit another 0. But once you get it down to this, you can probably just use elementary algebra techniques to take you the rest of the way. So that's what I'm going to do. I'm going to abandon synthetic division now and find the other 2 remaining zeros by solving the 2nd degree equation here. So what we have to do is we have to solve this other 2nd degree equation, 3x squared plus 4x minus 4 equals 0. And I don't know, I mean, does this thing factor here or not? Can we factor this trinomial here, ladies and gentlemen? Of course, you can use your grouping method or your trial and error method. The bottom line is we have to get this completely factored. And after thinking about this and pondering over it, hopefully you do get the factorization of that to be 3x minus 2 times x plus 2. I think this works. 3x times x is 3x squared. 3x times 2 is 6x minus 2x is 4x. And negative 2 times 2 is negative 4. That would be the factorization on that left side, that difficult trinomial. Now we set these factors equal to 0, and then what? Find our other two zeros by solving the equations. So therefore, we set 3x minus 2 equal to 0, solve for x, and ladies and gentlemen, another 0 would be 2/3. And then we set our other factor, x plus 2 equal to 0. Solve for x, and we get negative 2 as being our last 0, and we are done. We have found all our zeros for this fourth degree polynomial. They are negative 1, 3, negative 2, and positive 2/3. I got a question. Are all these zeros, which are rational zeros, are they in our P over Q list? Are they in here? They better be in here. Are they all in here? We got
Yes,
positive
sir.
2/3, right? You got negative 1, you got 3, you got what? Negative 2, agree? They're all in this list? Everybody see that there? All right. Any questions, ladies, on how we're finding zeros of a polynomial function? Not only do we find all the zeros of this thing, we could now write this thing in completely factored form. So therefore, d of x in completely factored form, if negative 1 is a 0, if negative 1 is 0, then x minus a negative 1 must be a factor. So x minus a negative 1 must be a factor. If 3 is a 0, then x minus 3 must be a factor. If negative 2 is a 0, then x minus a negative 2 must be a linear factor. If 2/3 is a 0, then x minus 2/3 must be a linear factor. Do you agree? We completely factor that fourth degree polynomial all the way down in linear factors. So this would be the complete simplified factorization of d of x. It would be x plus 1 times x minus 3 times x plus 2 times x minus 2/3. What's the sum of all these multiplicities, ladies and gentlemen? Negative 1 occurs as a 0 one time. 3 occurs as a 0 one time. Negative 2 occurs as 0 one time. And 2/3 is a 0 that occurs one time. So the multiplicities of all these zeros here, these 4 zeros are all 1. The multiplicities are 1. So let's sum up all the multiplicities. 1 plus 1 plus 1 plus 1. Does the sum of the multiplicities equal the degree of the polynomial? Is that true?
Yes.
That is true. And that theorem, fundamental theorem of algebra, guarantees that the sum of the multiplicities of all the zeros of a polynomial function better be equal to the degree of a polynomial function. And that's true. All these theorems are holding true. They have to. They're theorems. They're proven valid statements in mathematics, ladies and gentlemen. They've been proven and scrutinized. So they are valid and proven to be valid in all cases. Okay? They're theorems. All right. That was number 18. What do you think about this? You think you might have any success with these? Oops, what was that? So finding zeros of polynomial functions. Okay. Now, I'm going to jump down here to a problem like number, let's see if there's an easier one here. No, there really isn't. I'm going to jump down to one like number 34 here, ladies and gentlemen. This is problem 34 is on page, whatever, page 341. Page 341, number 34. What they want you to do with these problems here is the instructions are up here. It says A, find all the zeros. B, factor f of x as a product of linear factors. C, solve the equation f of x equals 0. Well, ladies and gentlemen, if you solve that equation f of x equals 0, that means you're going to get all your zeros. because all your zeros are solutions to that equation in part C. So by doing part A, we will also be answering part C, okay? All right, now here's the beauty of this problem. They're gonna help you out. They're gonna give you a little jump start, ladies and gentlemen. They're gonna tell you a zero of the polynomial function, and they want you, therefore, using that given zero, they want you to find all the remaining zeros. So notice for this 4th degree polynomial function in problem number 34, they give us one of the zeros as 3 minus I. We have to therefore find the other 3 remaining zeros. So how are we going to do that? Well, first we're going to write it down. And then what are we going to do?
Use synthetic division.
All right, what am I going to synthetically divide into the coefficients of my polynomial?
3 minus I.
We're literally going to divide in that 3 minus I. And when we divide that 3 minus I into the coefficients of this 4th degree polynomial, we better expect its remainder to be equal to what? What has the remainder have to be equal to?
0.
0, because they tell you that's a 0, okay? All right, so here we go, ladies and gentlemen. Now, when you do this, you're probably gonna have to turn your paper from portrait view to landscape view, because you're gonna need a lot of lateral territory on your paper when you start dividing in complex zeros synthetically, okay? Trust you me. What was it again? What was our complex zero? Was it 3 minus I or 3 plus I?
3 minus I.
All right. So we're going to divide 3 minus I now into the coefficients of this 4th degree polynomial, and they would be 1. Leave some lateral space between the coefficients. You'll see why. 1 and then -6. And then +5. Notice I'm leaving a lot of space in between my coefficients. +30 and -50. All right, here we go. Bring the 1 down. Ladies and gentlemen, when I get done dividing 3 minus I into this polynomial, I better get a 0 remainder here at the end. I better, because they tell me that this has to be a 0. So we better get a 0 remainder by the remainder theorem, okay? All right, so what's 3 minus I times 1? That's going to be 3 minus I. And now we got to add these together. What's -6 plus 3? -3 minus 3 minus I. Now we got to take 3 minus I and multiply it by -3 minus I. To do this, you might want to do this off to the side of your paper. Take the 3 minus I and multiply it by the -3 minus I. We're going to have to FOIL this out. What's 3 times 3? 3 times -3, excuse me.
-9.
What's 3 times -I? -3I. What's -I times -3? +3I. What's -I times -I? -I times -I is +I squared. Combining like radicals. What's -3I minus 3 plus 3I? What happens to the i's?
Cancels out.
They're gone. They're gone. We're left with -9 plus I squared. But what's I squared by definition?
-1.
-1. So -9 minus 1 is -10. So after I multiply 3 minus I times -3 minus I get -10. Bring it up. And now add. What's 5 plus a -10?
-5.
Now we have to take 3 minus I and multiply it by -5. And then we'll bring that up here. So, we could probably do this without going off to the side of our paper. What's 3 times -5? 3 times -5.
-15.
-15. And what's -I times -5?
Plus 5I.
Plus a 5I, you agree? Add these together. Remember, when we add complex numbers together, we are only able to add the real parts together and the imaginary parts. 30 plus a -15 gives us 15. All right, now we have to multiply these together. Ladies and gentlemen, what do you think the product of these had better be? When I multiply these together, I better
50.
get what? I
50.
better get +50? Because I got to get a 0 remainder. Do you agree?
Yeah.
Convince ourselves. Take the 3. Oh, hold on a second. I don't want to burn that space. take the 3 minus I and multiply it by this 15 plus 5I. Let's convince ourselves that we get 50. 3 times 15 is 45. 3 times 5I is 15I. Negative I times 15 is negative 15I. Negative I times 5I is negative 5I squared. These drop out. And we're left with 45. Now, negative 5 times I squared is negative 5 times negative 1, which is plus 5. Guess what we get? We get 50, just as anticipated. We get a 0 remainder. We should not be surprised or shocked that we get a 0 remainder, because they told us that 3 minus I was a 0 of this polynomial. We would expect that. All right, now, ladies and gentlemen, do you remember that conjugate pair theorem we read off? That conjugate pair theorem says that if 3 minus I is a 0, what is automatically another 0?
3 plus I, or negative 3 plus I.
No, 3 plus I.
Okay.
Remember, complex zeros always come in conjugate pairs. So if 3 minus I is a 0, 3 plus I, the complex conjugate of 3 minus I, also has to be a 0. This must be a 0. So when we get done dividing this in, which we will get a 0 remainder. What's 3 plus I times 1? That gives you 3 plus I. Notice I lined up my real parts and imaginary parts. Now we add them together. The real parts add up to 0. The imaginary parts add up to 0. Heck, we're left with 0, aren't we? Now, 3 plus I times 0 is 0. Negative 5 plus 0 is negative 5. Now, what's 3 plus I times negative 5? What's 3 times negative 5?
Negative 15.
What's I times negative 5?
Negative 5.
Now, when you add these together, what do you get?
0.
0. And that's exactly what we should be getting, because we've already used that complex conjugate pair theorem that says that if 3 minus I is a 0, this automatically has to be another 0. And that's why we get a 0 remainder again. By now, I got my function down to a what degree function, ladies and gentlemen. I performed 2 divisions. So I've knocked it down from degree 4 down to degree number what? 2. Do you agree? We got it down to a 2nd degree polynomial. So I'm going to abandon synthetic division now, and I'm going to write down what my remaining polynomial is. It would be 1x squared plus 0x minus 5. So this is your remaining what? This is your remaining polynomial that you have left. So therefore we have x squared minus 5 left. To find the other 2 zeros, we set this equal to 0 and now solve this quadratic equation. To solve it, we will employ the square root method, which means we isolate the squared term on the left first by adding 5 to both sides. We take the square root of both sides. And so it looks like our 2 other irrational zeros would be what? Positive or negative square root of what? 5. And we are done. And so, ladies and gentlemen, we have found all the zeros of this polynomial function. The zeros are 3 minus I, 3 plus I, positive square root of 5, negative square root of 5. We have 4 zeros, 1, 2, 3, 4, each with multiplicity of 1. They all occur one time. Notice the number of zeros we have is equal to the degree of our polynomial, or the sum of the multiplicities is equal to the degree. Furthermore, they want you to write this polynomial in completely factored form in the product of linear factors. Well, if the square root of 5 is a 0 by the factor theorem we touched base with 2 days ago, it must be true that x minus the square root of 5 is a factor. If negative 5 is a 0, x minus a negative 5, ladies and gentlemen, or x plus 5 must be x plus the square root of 5, must be a 0. If 3 minus I is a 0, it must be true that x minus this 3 minus I must be a factor. If 3 plus I is a 0, which it is, x minus 3 plus I must be a linear factor ladies and gentlemen, we have torn down this fourth degree polynomial and completely factored it into the product of 4 linear factors. And we're done. Everybody see what just happened there? So using the given 0, we were able to find all the other zeros, all of the other ones. Able to find all the other zeros. And then once finding all the zeros, we were able to then completely factor our polynomial down into the product of linear factors. So is this making any sense here, ladies and gentlemen?
Yes.
Go back here and see if we can maybe show you one here. All right, let's see here. Okay, I'm gonna show you a problem up here. I'm gonna have you try one for the class work number 1. Notice here, ladies and gentlemen, this problem number 26 here. It's a 3rd degree polynomial function. See number problem 26, everybody? All right, this is gonna be classwork number 1. I'm gonna tell you one of the zeros of this polynomial function. Ladies and gentlemen, 4 is a 0 of this polynomial function. I want you to find the other 2 zeros. So problem number 26, I'm gonna give you one of the zeros, which is 4, and I want you to find the other 0. So we'll call this classwork 1. Today is October what? 27th. Problem 26 here, which says that we have a polynomial function p of x, which is a 3rd degree polynomial function. And we want to find all the zeros. If x equals 4 is a 0. Okay, so here's your classwork number 1. If x equals 4 is a 0, I want you to find the remaining zeros. And then part B, I want you then to factor P of X. Factor P of X into linear factors. Go ahead, ladies. I'm going to give you time to work on this. This is called classwork 1 here. All right, go ahead. That should be a pretty easy problem. Anybody need more time on this problem? Well, ladies and gentlemen, if 4 is a 0, then if I divide 4 synthetically into the coefficients of this third degree polynomial, I better get what for a remainder?
0.
Better get 0. 4 times 1 is 4, add, you get -4. 4 times -4 is -16, add, you get 13. 4 times 13 is 52, add, 0 remainder. That's exactly what we anticipated. Now to find the other 2 remaining zeros, notice we performed one division by x minus 4. Hence, ladies and gentlemen, we got this down to a second degree polynomial because we already factored out x minus 4. We've already factored out x minus 4. So we got it down to a second degree polynomial. Here would be the remaining polynomial, 1x squared minus 4x plus 13. Now to find the other 2 zeros, we would set this equal to 0. Ladies and gentlemen, we would set this equal to 0 and solve the other and find the other 2 zeros. There's got to be 3 zeros for this thing. Now, are we lucky enough to be able to factor this trinomial? Doesn't look good, does it? It doesn't look like it's factorable. So we can either complete the square on this to solve it or use the quadratic formula. And therefore, I will opt for the quadratic formula. So my A is 1, my B is -4, my C is 13. Here's the quadratic formula. We take the opposite of B, which is the opposite of a -4, plus or minus the square root of B squared, which is -4 squared, minus 4 times A times C, and all this is divided by 2 times A. All right, quadratic formula is going to solve for the 2 roots for this second degree equation here. We have 4 plus or minus the square root of -4 squared is 16, and -4 times 13 is -52, and that sits over 2. What's 16 minus 52?
-36.
-36. And what's the square root of -36? 6 what? 6i? So we have 4 plus or minus 6i divided by 2. Feel free to reduce. 4 over 2 reduces down to 2. Plus or minus 6i over 2 reduces down to 3i. Ladies and gentlemen, you got your 2 other zeros. They're complex. 2 plus 3i and 2 minus 3i. So all the zeros for this polynomial function for part A, the zeros are 4, 2 plus 3i, and 2 minus 3i. There's your 3 zeros for your third degree polynomial. Now that we have all the zeros, we can write this in completely factored form. So this will be part B. This function P of x factors down into x minus 4. If 2 plus 3i is a 0, then x minus 2 plus 3i must be a factor by the factor theorem 2 days ago. And if 2 minus 3i is a 0 by the factor theorem, x minus 2 minus 3i must be a factor. And here's the complete linear factorization of this polynomial function P of x. There it is. And we're done. Anybody get that correct? Get both parts correct?
Yeah.
All right. Congratulations, ladies and gentlemen. This was a fairly simple one because, I mean, this polynomial only had 4 terms in it, unlike some which can have maybe 10 or 15 terms in them, which would, just take a little bit longer, that's all. All right. So we come a long way since our days in elementary algebra, because in elementary algebra, we would not even know how to factor this down into this. We wouldn't even be able to get started on this. There's nothing you can do. Grouping doesn't work here. Grouping fails, ladies and gentlemen. You can't factor this by grouping. You see, elementary algebra falls flat on its face with a problem like this. But now we're in college algebra. We're more sophisticated. Okay. All right. Ladies and gentlemen, there is another theorem in this section here. It's called Descartes' rule of signs. Descartes was a French mathematician, ladies and gentlemen, and I may not even be pronouncing that correctly. It's called Descartes' rule of signs, and let's go up and touch base with this very important theorem here. This theorem is found on page 336 in section 3.4. Notice your theorems are always in purple boxes. It's called Descartes' rule of signs. It says, let f of x be a polynomial function with real coefficients and a non-zero constant term. Then this theorem says this. Number one, the number of positive real zeros that this polynomial function has is either the same as the number of sign changes that can be counted in f of x, or less than that number of sign changes in f of x by a positive even integer. All right. Number two, the number of negative real zeros is either the same as the number of sign changes in f evaluated at negative x, or is less than that number of sign changes by a positive even integer. So what this theorem is guaranteeing, ladies and gentlemen, is it's basically enabling us to determine how many positive real or negative real zeros a polynomial function has based on this concept of sign changes. Right now, this theorem is about as clear as mud in your minds, but I'm going to show you an example that'll breathe life into this theorem and bring it from the dead back to life, ladies and gentlemen. So let's look at a problem that illustrates the use of this Descartes' rule of signs. All right. And so what we're going to do is we're going to apply it to this example here. So this is an example illustrating Descartes' rule of signs. And we're going to use this fifth degree polynomial function here. X to the fifth minus 6x to the fourth plus 12x cubed minus 12x squared plus 11x minus 6. A 6-term polynomial. Okay, now, ladies and gentlemen, what does Descartes' rule of sign guarantee here? It's called Descartes' rule of signs. You know, I did not have any French, ladies and gentlemen. I had a couple semesters of Spanish, but not French. But has anybody had French? I think this S would be silent. Is that correct? Would we say Descartes? Descartes? Anybody have French before? Anybody?
I did, but it was so long ago.
All right. I don't know. If I had to guess, if my life depended upon it, I would think this S is silent. I would say Descartes. Descartes. Okay.
Yeah, I'm pretty sure that the S is silent. I'm not a
Sounds
professional or anything, but I'm pretty sure that it's silent.
Yeah, I mean, that's how I've been pronouncing it, you know, Descartes. I mean, I just don't think that S would be heard in French, but I could be wrong. Okay, anyways, Descartes' rule of signs, this apply that theorem to this function here, and this is how it works. What we do, ladies and gentlemen, we look at f of x here, and we look at the signs of the terms, okay? My first term is of what sign, positive or negative? I don't care about the details. I'm just concerned about the sign. Is this a positive or a negative term?
Positive.
It's a positive. This is a what? A negative term. This is a positive term. This is a negative term. And this is a positive term. And this is a negative term there. Okay. Now we're going to count how many sign changes we experience from left to right. We go from a positive to a negative. We're going to keep count over here. Positive to a negative, that's one sign change. We go from a negative to a positive, that's another sign change. We go from a positive back to a negative, that's another sign change. We go from a negative back to a positive, that's another sign change. And we go from a positive to a negative. Ladies and gentlemen, we've experienced 5 sign changes here. Do you agree? 5 sign changes. So, Descartes' rule of signs theorem guarantees that f of x will have 5 positive real zeros or this number decreased by an even number 2, or it could have 5 minus 2 or 3 positive real zeros, or 5 decreased by the next even integer 4, or we could have 5 minus 4 or 1 positive real zero. Okay, that's what Descartes' rule of signs guarantees for this 5th degree polynomial function. It will have either 5 positive real zeros, or 3 of them, or 1 of them. Now, we're going to look at this function evaluated at negative x. We'll put negative x in. Wherever we see x, we replace it with negative x. Then we'll simplify and then recount the sign changes. So we put negative x in here, 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 and here. Simplify and here, and simplify, and then we'll count the sign changes again. So I have negative x to the 5th minus 6 times negative x to the 4th plus 12 times negative x cubed minus 12 times negative x squared plus 11 times negative x minus 6. All right, let's simplify after having made this substitution. When a negative raised to an odd power is still a negative, this will still walk out of here as being negative x to the 5th. This is going to be a positive x to the 4th times negative 6 is minus 6x to the 4th. This is going to be a negative x cubed times 12 minus 12x cubed. This is going to be a positive x squared times negative 12 minus 12x squared. This is going to be a negative x times 11 minus 11x minus 6. Now, ladies and gentlemen, we count the sign changes again. We go from a negative term to 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 a negative term. How many sign changes do we count? Negative to a negative is no sign change. Negative to a negative is no sign change. No sign change. No sign change. Negative to a negative, no sign change. There's no sign changes when we
But
evaluate.
why wouldn't the sign for the second 12 not change?
For
Like
for this one here.
yeah.
Okay, a negative x times a negative x, ladies and gentlemen, is a what? Positive x squared.
Oh, I
Yes.
misread that.
And a positive x squared times a negative 12 is a what? Still a negative 12x
Negative.
squared? Still negative, isn't it?
Yep.
Okay, still negative.
Yeah, thank you.
So there's no sign change. And ladies and gentlemen, since there's no sign change, Descartes' rule of signs theorem guarantees that f of x will have 0, because there were 0 sign changes, 0 negative real zeros. So this polynomial function will have 0 negative real zeros. In other words, there's not going to have, this thing's not going to have any negative real zeros. There's no negative real zeros. That's how Descartes' rule of signs works here. So Descartes' rule of signs says that this 5th degree polynomial function will have either 5 positive real zeros, or 3 of them, or 1 positive real zero, but it's not going to have any negative real zeros. Okay, because there were no sign changes here. By the way, ladies and gentlemen, for this second part of Descartes' rule of signs, if you had a placeholder in here, like if you had to put like a 0x cubed in here, a zero could be counted either way for a sign change. For instance, if this went from a negative to a negative and then it went to like 0x cubed, then you could call that 0x cubed a positive to try to maximize the number of sign changes in here. So if I had a placeholder 0x cubed, I would have no sign change here, but then I would have 1 sign change here, because I could consider that 0 to be a positive, and then a positive back to a negative, that'd be another sign change. And we understand what I just said there? If you ever have any placeholders you got to put in here, if you're missing any powers of x, ladies and gentlemen, you can count them either as a positive or a negative, okay, to maximize the number of sign changes in f of negative x. That's what I'm saying. All right. All right. So let's build a table here and try to assess, ladies and gentlemen, what kind of zeros we would expect for this 5th degree polynomial function. So positive real zeros, negative real zeros, non-real. Non-real means complex, where you would see I. Zeros. And then we're gonna have a total roll down here. Make a little table here. What was the degree of my polynomial function? It was a what? A fifth degree. Do you agree? So how many zeros must this thing have, ladies and gentlemen, totally?
5.
It's going to have 5 zeros. Okay. Notice, according to Descartes' rule of signs, we could have what? 5 positive real zeros. So, ladies and gentlemen, we could have 5 positive real zeros. But if we have 5 positive real zeros, that means all the zeros have been accounted for this fifth degree polynomial function, which means that you could not have a negative real zero. You could not have any complex zeros. Notice the sum of these gives you the degree of the polynomial, 5 zeros. But ladies and gentlemen, Rene Descartes' rule of signs says that we could have, instead of 5 positive real zeros, we could have 3 positive real zeros, which means we could have 3 positive real zeros. But if we have 3 positive real zeros, could I have any negative zeros?
No.
No, Descartes' rule of signs says there will not be any negative real zeros. Okay, so there's still no negative real zeros, but we only accounted for 3 zeros. There's still got to be 2 other zeros. So, ladies and gentlemen, what does that mean for the complex number of complex zeros we would have to have?
You'd have to have 2.
We'd have to have 2. Why do you think this is an even number for complex zeros?
Complex conjugates.
Because the complex conjugate theorem says that if you have complex zeros where you have I, they must always come in pairs, ladies and gentlemen. So if 2 plus 3i is a 0, 2 minus 3i automatically has to be another 0. Notice he's at up to the degree of our polynomial. But Descartes' rule of signs says we could have maybe only 1 positive real zero. Another possibility is we could have 1 positive real zero, 0 or no negative real zeros. But if we only accounted for 1 of the 5 real zeros, that means we'd have to have how many complex zeros?
4.
4. Meaning you have to have 2 pairs of complex conjugate zeros. You agree? 2 pairs of them. Notice this adds up to 5. Does that make sense, ladies and gentlemen, as to the potential type of zeros this fifth degree polynomial could have? This is the potential type of zeros for f of x. It's the potential type of zeros for f of x. Well, here's what I did. In my spare time, which I really don't have much of, but in my spare time, ladies and gentlemen, I actually found all the zeros for this polynomial function. I took the time to find all the zeros for this fifth degree, 6-term polynomial function. And I'm going to walk you through all these zeros here. The first zero I found was 1. I'd used my rational zero theorem. I put together my list of potential zeros. Okay. And by the way, what would be our P list? This should be pretty simple here. My P list would be all the factors of -6. You know, an easy way to remember this, ladies and gentlemen, is P comes before Q in the alphabet. Do you agree? P comes before Q, but it's just the opposite when you put them in your polynomial. So P comes after Q as far as which one's the list of coefficients of which. So P comes before Q in the alphabet, but P is the list of factors of the constant terms that comes after the list of the leading coefficient. So what are all the factors of -6? Positive -1, negative positive 6. Why do I have negative positive? Why did I invert these signs here? Negative positive. Because what's a positive 1 times a -6? It has to give me a what? A -6. What's a -1 times a positive 6? It has to give me a -6. Positive -2 multiplied by what? Negative positive 3 are factors of -6. What are the only factors of positive 1, our leading coefficient? Positive -1 times itself. So ladies and gentlemen, what's my P over Q list? My P over Q list duplicates what list?
The P list.
The P list. You take each of these and divide it by positive -1, you're just going to duplicate the P list. So positive -1, positive -2, positive -3, positive -6. So the rational zero theorem guarantees that if my fifth degree polynomial has any rational zeros, they must come from this list. I tried one first and it worked. So ladies and gentlemen, I'm going to show you that one will work. I divided one synthetically into the coefficients of this fifth degree polynomial. One times one is one, add, you get -5, multiply, you get -5, add, you get 7. 1 times 7 is 7, add, you get -5, multiply, you get -5, add, you get 6, multiply, you get 6, add, you get a remainder of 0. Everybody see that there? You gotta love synthetic division. Look at how quick it is. It's a lot quicker than long polynomial division. Okay. Ladies and gentlemen, I then tried 2. Do you agree? One's in my list. Oh, excuse me, one's in my list. It's there. Try 2. 2 works. I found 2 to work. 2 is another 0. 2 times 1 is 2. Bring the number up and add. You get -3. 2 times -3 is -6. Bring it up, add. You get 1. 2 times 1 is 2. Bring it up, add. You get -3. 2 times -3 is -6. Add. You get the expected remainder of 0 because I told you 2 was a 0. We found 2 of the 5 zeros. There's 3 more. Well, to find the other 3, ladies and gentlemen, I got it down to now a 3rd degree polynomial because I did 2 divisions from a 5th degree polynomial. So I got this down to a 1x cubed minus 3x squared plus 1x minus 3. I then found my 3 other zeros by setting this equation equal to 0, now solving this 3rd degree equation. Grouping enables me to factor this, ladies and gentlemen. This factors by grouping. Trust you me, it factors by grouping. I'm just going to put the factorization down here. If you did grouping on that, you would get x squared plus 1 times x minus 3. So that left side factors completely into this. We now set both factors equal to 0. And we find our remaining zeros. Adding 3 to both sides to solve this equation, we get another 0, which must be 3. 3 is another 0. Subtracting 1 from both sides, we get x squared is equal to -1. Take the square root of both sides, ladies. I'm going to solve this quadratic equation, and you get your 2 other zeros, which would be plus or minus what? I. Square root of -1 is I. You got your other 2 zeros. So let's list all the zeros of this polynomial function. What were all the zeros? 1, 2, 3, positive and negative what? I. Ladies and gentlemen, which scenario, which column panned out for this 5th degree polynomial as far as the type of zeros is concerned? First, second, or third column?
The second.
The second column. That's exactly what transpired here. So René's Descartes' rule of signs says that, yes, this 5th degree polynomial could have 3 positive real zeros. We got them, 3 positive real zeros. Or it could have, and it can have what? 2 complex conjugate zeros. There they are. Does that make sense? René Descartes' rule of signs, ladies and gentlemen, how it's applied and what it can tell us about the potential types of zeros that a polynomial could have. Okay, that's Descartes' rule of signs. And I've been using that first word of René because that was the mathematician's first name, ladies and gentlemen. René Descartes was a famous mathematician, a French mathematician who came up with this theorem. Quite amazing to come up with a theorem in mathematics. I've never done so yet in my lifetime, and I probably won't. I'm just trying to relay the information. I stand on the shoulders of giants, ladies and gentlemen. I stand on the shoulders of giants that preceded me. René Descartes' rule of signs. All right. So that's pretty cool how that works there. All right. Okay, maybe we can go to our textbook and who knows, maybe apply the rule to one of these here. Let's go down to our homework problems here and see if we can apply René Descartes' rule of signs here to maybe a problem here. Here we go. Apply Descartes' rule of signs, problems 49 through 56. They give you polynomial functions, ladies and gentlemen, and they want you to try to predict the number of possible positive and negative real zeros for the given function. I'm going to choose one that has me putting in a placeholder. Hold on one second. Let's see. Can we see one where we're going to have to put a placeholder in for X? Do we see one in here anywhere?
52.
52, we'll do 52. Because I want to try to clarify what I said about placeholders and counting the sign changes. So number 52, we'll try this problem out of your textbook in section 3.4. Now notice h of x is not written in descending order. Yes, it is. I said corrected. Negative 4x to the 9th plus 6x to the 8th minus 5x to the 5th minus 2x to the 4th plus 3x squared minus x plus 8. And what we're going to do is apply Descartes' rule of signs to try to predict how many positive or negative real zeros this polynomial will have. Notice we're not being asked to find the zeros. It doesn't say that. They just want us to predict how many positive or potential negative real zeros this thing would have. All right, so here we go, ladies and gentlemen. Let's see if we can predict this here. Let's count the sign changes as is. We have a negative term, we go to a positive term, a negative term, a negative term, a positive term. Wait a minute. I forgot to put in my what? What did I forget, ladies and gentlemen? Yeah, my placeholders. I forgot to put my placeholders in, and there's quite a few. We're not ready for Descartes' rule of signs yet. My apology. Okay, here we go. Yeah, we got to put some placeholders in here. We have a 9th degree term here, and then we go from a 9th degree term down to an 8th degree term. That's cool. Then we go from an 8th degree term down to a 5th degree term. Oh boy, we're missing a 7th degree term. We're missing a 6th degree term. Now we go down to our 5th degree term. We're missing a 3rd degree term, another placeholder. We got a second of, we have a, we don't need the placeholder here. We got a 5th degree term. We got a 4th degree term. We don't have a 3rd degree term. Now we put the 3rd degree placeholder term in here, and then we go down to a 2nd degree term. Then we go down to our 1st degree term, and we have our constant term at the very end. There we go. See all the placeholders there? All right, so ladies and gentlemen, sign changes. We go from a negative term to a positive term. Oh, but wait a minute, ladies and gentlemen, what do we got here for these zeros here? Wait a minute here. How do we count those, or what do we do with those? We better go back and take a snapshot of that Descartes' rule of signs. Where is that theorem? Right here? Now, as far as zeros are concerned, ladies and gentlemen, it's where was that darn thing here? Yeah, as far as zeros are concerned, what are we going to have here? Because we had to put some placeholders in there. Well, what I got here for placeholders on Descartes' rule of signs is as far as if we got placeholders in here, I think it only applies to the negative real zeros. I don't think it applies to the positive real zeros. This is problem what, number 52, is that correct?
Yes.
All right. Tell you what, let's go back to our original polynomial here. And let me take a quick quick peek here, ladies and gentlemen, as to the result for this. This is section 3.4. Hold on a second here. And this is problem number 52. Let me take a quick look so I don't steer you wrong here. What the? Hold on a second. What's going on here? Number 52. Must have had the answer appendix here. I'll be darned. For problem 52, they're not showing 52. So Hold on one second. 4. Number 52. Okay, all right. Okay, so we're gonna see how many sign changes we have here. These zeros, the jury's still out on those, ladies. I'm gonna come back in a second. And this is a negative sign term, negative sign term, and this one we don't know yet. I'll come back to it. This is a positive, this is a negative, this is a positive. How many sign changes do we count as is if we did not put anything in for the zeros? We'd have 1 sign change, 2 sign changes, no sign change, still 2, 3 sign changes, 4, and 5, correct? Okay, the way it works, ladies and gentlemen, for Descartes' rule of signs here, it does not apply, zeros or placeholders do not apply for the first part of Descartes' rule of signs as far as positive zeros are concerned. And so when we have placeholders in here, okay, we consider the sign to be neutral, neither negative or positive. We don't put any signs in here. We just count these sign changes here. So we have 1 sign change. That's 1. We go from a positive to a negative. That's another sign change. That's 2. We go from a negative to a negative. That's not a sign change. We go from a negative to a positive. That's a sign change. We go from a positive to a negative. That's a sign change. And a negative to a positive. That's the 5th sign change. Okay. So by Descartes' theorem, ladies and gentlemen, we would say that h of x has 5 positive real zeros, or could have 5 decreased by an even integer 2. 5 minus 2, or could have 3 positive real zeros, or could have 5 decreased by the next larger even integer, which is 4. So 5 minus 4 is, it could have 1 positive real zero. So notice you always decrease this by a positive integer. So 5 minus 2 gives you this possibility, or 5 minus 4 gives you the next possibility. Once you get down to 0, ladies and gentlemen, or go below 0, you never include any negative possible number of positive or negative zeros. It's no such thing as saying like there's a negative 2 number of positive real zeros. So you keep taking this number down by an even integer, down by 2 first, then down by 4, then down by 6, down by 8, whatever, until you get down to 1, or you get down to 0, and then you stop. Okay, because in other words, I could have counted 4 positive 4 sign changes, in which case if I counted 4 sign changes, there would be a possibility of 4 positive real zeros, or 4 minus 2, or 2 positive real zeros, or 2 minus 2, or what? 0 positive real zeros. So you always decrease this by an integral multiple of 2, okay, until you get down to 1 or 0, and then you quit. All right, now for the negative real zeros that this potentially could have, what we want to do is we want to evaluate our function at negative x, which means that wherever we see x, we have to replace x with negative x, and then simplify, and then do a sign change count once again. So, you know, in for these placeholders, ladies and gentlemen, they're still going to be 0, you know, regardless of what you put in for x here. Minus 2, negative x to the 4th, plus 0, x, negative x to the 3rd. Oh gosh, let's see, running shy of room here. I'm going to wrap around here and say negative 1 times negative x, and then we got positive what, 8 here. Okay, this was 3x. We need our second degree term here. We got to have our 3 times negative x squared in here. All right, and then we got that. Okay, so we simplify here, and h of negative x therefore is going to simplify. This is going to be still negative This is still going to be negative x to the 9th times negative 4 is going to be a positive 4x to the 9th. This is going to be x to the 8th power, positive x to the 8th times 6 is plus 6x to the 8th. This is going to be 0. This is going to be 0. This is going to be negative x to the 5th times negative 5 is now plus 5x to the 5th. This is going to be x to the 4th times negative 2 is negative 2x to the 4th. This is going to be negative x cubed. We don't care because times 0, it's still 0. 0x cubed. This is going to be negative x squared is x squared times 3 is plus 3x squared. Negative x times negative 1 is plus x. And then we got the plus 8. All right, so we count these sign changes. This is a positive, positive. Now, for evaluating the function at negative x, the way it works for the second part, for finding negative zeros here, ladies and gentlemen, do we count these sign changes for these zeros here? Do we count these sign changes for these zeros here? And the answer is no. I have Descartes' rule of signs confused with what's called the upper and lower bound theorem, that I did not show you yet, as far as letting 0 take on a sign of a positive or negative. With Descartes' rule of signs for both parts, for finding positive zeros and negative zeros, when you have 0 placeholders, you don't assign them any sign. You just skip over them. So we skip over these, and then we go to a positive term, negative term, skip this, positive term, positive term, positive term. Now we count all the sign changes. So how many sign changes do we get here? Well, this is not going to be a sign change. Positive to a positive, positive to a positive, no sign change. Positive to a negative, that's one sign change. Negative to a positive, that's a sign change. Positive to a positive, no sign change. Positive to a positive, no sign change. There's two sign changes. So the theorem guarantees that we're going to have two negative, there was two sign changes, two negative real zeros. Or, ladies and gentlemen, we could have, what's 2 minus 2? 2 minus 2. Or we could have 0 negative real zeros. Okay, so there you go. There's your possibilities. So we have just applied Descartes' rule of signs in predicting the number of potential positive real zeros or negative real zeros. You could have either 5 positive real zeros or 3 or 1, or you could you could have 2 negative real zeros or no negative real zeros. Okay. All right. So that's how that works there. Descartes' rule of signs. It enables you to predict the number of potential positive real zeros or negative real zeros that a polynomial function could have. Okay. All right, there is one last theorem in here, ladies and gentlemen. It's called the upper lower bound theorem. Here it is. It's on page 338. It's entitled the upper lower bound theorem for real zeros of a polynomial. It says, let f of x be a polynomial of degree greater than or equal to 1 with real coefficients, positive leading coefficient. Further, suppose that f of x is divided by a linear factor x minus c. It says if that number c is greater than 0, and if both the remainder and the coefficients of the quotient are non-negative, then c is an upper bound for the real zeros of f of x. In other words, ladies and gentlemen, there will be no other real zero for the polynomial function that's greater than c if c is an upper bound. So let's say c was like 3. Well, your polynomial function could not have any other real zero larger than 3. 3 is the upper bound or the ceiling, if you will, as to the type of real zero or the number, the type of real zeros that the polynomial function could have. Number 2, if that number c is negative, meaning less than 0, and the coefficients of the quotient and remainder theorem and the remainder alternate in sign, with 0 being considered either positive or negative as needed. There you go. I was confusing that with Descartes' rule of signs, which does not, allow us to do this. But with the lower bound, if you have a placeholder in the form of 0, you can count that zero either as a positive or a negative, whatever the case may be, to maximize the number of alternating terms in the quotient. If that's the case, ladies and gentlemen, if your signs of your coefficients of your quotient and remainder alternate in sign all the way across, then we would say C is a lower bound for the real zeros of f of x. So let's say that we determine that our lower bound is -2. That means that the polynomial function f of x would not have any real zero less than -2. That would be like a basement boundary, if you will. Okay. All right. So this upper lower bound theorem here. And I'm in the upper lower bound theorem. Let me see if I can demonstrate what that's saying here with an example. Okay. So the upper or lower bound theorem. All right. Suppose, we have this polynomial function f of x is equal to 2x to the 5th plus x to the 4th plus 9x squared minus 32x plus 20. Okay. I'm going to show that x equals 2 is an upper bound for the real zeros of f of x. So I'm going to show that. I'm going to demonstrate that by using this upper bound theorem. All right, so this is how it works. We synthetically divide 2 into the coefficients of this polynomial function. And notice we don't have any need. Wait, do we have to put placeholders in here?
Yes.
No, we need a, yeah.
The third degree.
We're missing a third degree power placeholder, third degree term. So 2, 1, 0. You got to put a placeholder in here, 0x cubed. So 0, 9, -32, and what? And 20. Okay. Everybody see that there? All right. Now here we go, ladies and gentlemen. We're going to synthetically divide 2 into these coefficients. Here we go. 2 times 2 is 4. Bring this up and add. We get 5. 2 times 5 is 10. Bring this up and we add. We get 10. 2 times 10 is 20. Bring this up and we add. We get 29. 2 times 29 is 58. Bring it up and we add. We get 26. 2 times 26 is 52. We add, we get 72. Now, how do I know that 2 is an upper bound for the real zeros, ladies and gentlemen, of this polynomial function? Let's go back to that theorem. It says, if c is greater than 0, which my 2 is greater than 0 that I divided in, and if both the remainder and the coefficients of the quotient are non-negative, then c is an upper bound. Do you agree, ladies and gentlemen, that all my coefficients of my quotient polynomial are non-negative, meaning they're positive? All positive. And do you agree my remainder is positive? Therefore, hence we can conclude that x equals 2 is an upper bound for the real zeros. For the real zeros of f of x. So I have a question for you. Do you think I could find the zeros of this polynomial function? Do you think that maybe 5 could be a real zero of this polynomial function? Could 5 be a real zero?
No.
No, can't be. Because they tell us the upper bound on the real zeros, ladies and gentlemen, is 2, positive 2. You're not going to have any real zero that's greater than positive 2 for this polynomial function. That's what the theorem predicts. Okay. Now, how about a lower bound? Well, I'm now going to show I'm now going to show that x equals -3 is a lower bound. A lower bound for the real zeros of f of x. To do that, ladies and gentlemen, we divide synthetically -3 into our coefficients. 2, 1, 0, 9, -32, 20. Here we go. -3 times 2, -6. Add, you get -5. -3 times -5 is 15. Add, you get 15. -3 times 15 is -45. Add, you get negative what? Is that -36, I believe?
Yes.
-3 times -36, we get what? 108, I believe, 108. Add these together, what do we get? We get, what is that, 76, is that correct? I believe that's 76. -3 times 76 is going to give us -228, is that correct? Is that right? I think so. Now add these together and we get negative what? -208. All right, ladies and gentlemen, now it says if -3 is to be a lower bound, what must be true? If -3, which is less than 0, is to be a lower bound, and it says the coefficients of the quotient and the remainder have to alternate in sign, with 0, if you ever got 0, being considered either positive or negative as needed to continue the alternation in sign. Notice we did not get 0 anywhere in here, ladies and gentlemen, for the coefficients of our quotient polynomial. How many alternations in sign? Do we have alternation in sign throughout here?
Yes.
We go from a positive to a negative, back to a positive, to a negative, back to a positive, to a negative. Since these signs alternate all the way across, we would conclude that -3 is a lower bound of the real zeros of f of x, meaning that you're not going to have any real zero for this polynomial that's less than what? -3. Do you agree? It's not going to, you're not going to be able to find one because this is the lower bound. So what have we discovered? We've discovered that 2 is the what? Upper bound, and -3 is the what? Lower bound. You agree? You agree our real zeros, ladies, I'm going to have to lie what? In between these are real zeros. You're not going to have any real zero greater than 2 or any real zero less than -3. That's what the upper lower bound theorem guarantees. Okay. All right. Unfortunately, ladies and gentlemen, I have exhausted my time. I have gotten through the section. It was a struggle. A lot of theorems in that section. There's a lot of good examples. I would strongly recommend that you take some time outside of class in your busy schedules, ladies and gentlemen. Try to look through some of those examples in that section. Try to get something out of those examples. It's only going to help reinforce your thinking on this section. Maybe look at those theorems again, okay, and see how they're being applied through examples. All righty. Okay. So, ladies and gentlemen, I'm going to let you go. All you have to do is turn in that initial classwork we did and finding those zeros, that polynomial function. That'll be the classwork for today. And have a spectacular weekend, safe spectacular weekend. And hopefully I'll see you next week. Okay. I will update Alex with the homework problems. You know, I'm really leaning more heavily towards Alex. I don't know if I'm ever going to give any more textbook homework problems. I don't know. I might once in a while, but most of them are going to be coming from Alex, because if he gets snagged, you can look at a similar problem to see how your author works it out. That's why I like Alex. Okay. All right. Any other questions? Any other questions or concerns, ladies and gentlemen? If not, you have a great weekend.